Right, so then the Stefan's law, or Stefan-Boltzmann's law, which states that the total power radiated per unit surface area of a black body is directly proportional to the absolute temperature to the fourth power. So that is to say that power over area is proportional to T to the 4. And you can obviously state, like with any proportionality relationship, that P over A equals some constant times T to the 4. And that constant, sigma, is called Stefan's constant, and it has the value of 5.67 times 10 to the minus 8 per meter squared per Kelvin to the power of 4. Now, yeah, it's an interesting rule, that, isn't it? But it's pretty obvious at the same time. We can extend on it. We can say that power per unit area is sigma T to the 4. And we can say that given that the surface area of a sphere equals 4 pi r squared, and that the radiated power is approximately equal to luminosity, we can state that Stefan's law is more commonly expressed as L, the luminosity, equals 4 pi r squared sigma T to the 4. So Stefan's law shows that a star's luminosity is directly proportional to its radius squared, its surface area, and its absolute temperature to the power of 4. That's really important because the luminosity is one of the few things that we've got that we can actually observe about a star. And if we can know anything else about it, we can use that as one of the measures to help us work something out about it. So, yeah, knowing a star's luminosity is helpful. And we can use there are other ways to determine its approximate temperature as well. So this relationship is useful, but we need more information usually because it's like that classic Father Ted thing. How far away is it? Is it a small sheep that's close to you, or is it a normal size sheep that's really far away? You've got that confusion, haven't you? If you've never watched Father Ted or familiar with that reference, you're like, what is he talking about? Anyway, then you've got finally the Hertzsprung-Russell diagrams. Now, what these are is a statement of temperature and luminosity and how they're related. Now, we know that L is directly proportional to T to the power of 4, but we've just got stuff all over this thing, and the reason for that is that stars behave differently at different stages in their life. Now, we've got our main sequence down at the bottom here, and that main sequence band goes all the way from the bottom right, generally straight up to the top left, right? And with the smaller, lower temperature stars over here, with the larger, higher temperature stars over here. You'll notice that the smaller ones that are lower temperature have a much lower luminosity than those stars up here. We have large stars with very, very large luminosity, but of a low temperature, and these are our red giants and our red supergiants. And then we have very large stars that are very hot and very luminous, and there are blue giants, or our supermassive stars. Our white dwarfs are down here. They're very, very hot, but they're not that luminous because they're very small. And then if I was a black dwarf, I would slowly fade like that down, and eventually over to the nothing Kelvin at like an infinite amount of time from now. Obviously, nothing can ever get to 0 Kelvin, right? The luminosity axis can sometimes be put in terms of absolute magnitude, which is how bright something appears when you're a fixed distance away from it. And the temperature axis can sometimes be put in terms of the spectral class or colour, which usually goes from violet, indigo, blue, green, yellow, orange, red. From left to right on the bottom. Sometimes they put these axes on the top and down the right hand side, so you get like a 4-axis graph. And we can learn, or we can see the life cycle of stars on the HR diagram. So we find that lower mass stars tend to evolve up the main sequence and jump off that main sequence into the red giant's phase. Once they've finished in that red giant's phase, what they leave behind is a white dwarf, and then, as I said a minute ago, that will then eventually fade over time, but there isn't sufficient time yet. And then we have these high mass stars, which are born very, very massive, and they're born violently, and their lifespan is really short. They quickly go from being massive stars to being massive red supergiants, and then obviously after that they then explode. But we talked about that earlier, so let's quickly run through, because there's a lot of stuff here. Stars go from being nebula to protostars to main sequence. Main sequence is when the hydrogen nuclei fuse to make helium, and when gravitational balance is radiation pressure. You've got the red giant stars, which is when they eventually balloon out because they've stopped supplying the radiation pressure because the hydrogen runs out, kicks off helium, and then can't do any more, so then eventually fades away, leaving behind a white dwarf. It's just a hot, dense, ridiculously dense ball. They're prevented from further collapse by the electron degeneracy pressure. Alternatively, a big main sequence star could have turned into a red supergiant, which could have then eventually gone supernova after repeatedly forming heavier and heavier elements, which blows up and can leave behind in its wake a neutron star, which is just like a very, very high neutron matter planet, in effect. Like, it's a star, isn't it? It's like a solid mass thing. It's hard to consider it as a star, but a neutron star. And if it's got sufficient mass, it can overcome its neutron degeneracy pressure and collapse into a black hole, which is the condition where not even light can escape it. Excellent. And I won't go through everything again, but these are important that you're aware of what they mean. So have a look at those, and I'll ask you some questions on them next time I see you. Right, so excellent. Bye.